Hello. In this video, we're going to be talking about density curves and a specific rule that we can apply to normal curves. So you did some experiments at home with tossing a penny, you tried to stop your timer, and you also rolled a die. Okay, hopefully you had a chance to try those experiments so you have an idea of what happened. What I would like you to do right now is pause your video and make a prediction about what you think happened each time and draw a graph for each one. So in the first time you rolled a die, and you rolled it 3 times, you might have gotten all 6s or a 1, a 2, and a 3. If we did this many times, say we rolled a die thousands of times, we should get about the same number of 1s, 2s, 3s, 4s, 5s, and 6s. So our graph would actually look something like this, where we have the same number of 1s, the same number of 2s, 3s, 4s, 5s, and 6s. This is what we call a uniform distribution when it's straight across like that. It's called a uniform distribution. And generally, this is a density curve. We're going to be talking about density curves today. And density curves can look a variety of ways. A couple of things about a density curve is that it is always above the x-axis. So all of our data points here are going to be above the x-axis. And the area under a density curve is always 1. And that's going to become very useful to us. Okay, so if I looked at this density curve, this uniform distribution, I know that my median would be right here in the middle, and my mean would be right there close to the middle too. So my mean will be approximately the same as my median. The other thing that's really helpful specifically to a uniform distribution is finding the height. Now we have to remember that inside this blue box, the area equals 1. This blue box has a length of 6. So 6 times what gives me 1? Because if I'm finding the area of a rectangle, it's just length times width. So I want to know, what is this height? Well, 6 times 1/6 is what will give me an area of 1. So it might be helpful to label that over here on our y-axis. The height here is 1/6. The next experiment that we did is we tossed a penny, tried to make it land on our target. Some of you were probably really good and you got it really close to the target. Some of you might have had some values very far away. Would we have any values that are negative? We're measuring distance, so we wouldn't have any negative values. The lowest value you would have is 0 if you landed it directly on the target. So your graph is actually going to look something like this. And if we think back to our shapes that we discussed last chapter, this is skewed right because the tail is to the right. We started this discussion already. How do our mean and median compare in a skewed right distribution? So our median would be somewhere in the middle point where the area on each side is the same. And then your mean is going to be pulled towards that tail. We have those high outliers out here, those people who are really bad at tossing their penny and it was 100 centimeters away, or inches, 100 inches away. That's going to pull your mean up that direction. So in a skewed right distribution, your mean is always larger than your median. If it were skewed left, the opposite of that. You'd have outliers on the lower end, which would make your mean less. So your mean would be less than the median. And then the last thing you did is you took a stopwatch, or you probably used your phone, and you tried to stop it exactly on 5 seconds. Maybe some of us were really good and we stopped it right on 5 seconds. But we're going to have a few that are below and a few that are above, and some people got it way below because they were trigger happy, and way above because they were just moving slow that day. So our distribution would actually look something like this. Okay, this bell curve that we see here. Okay. In this bell curve, it is symmetric. So we could draw that line down the middle where it looks the same on both sides. And in a symmetric distribution, your mean is approximately the same as your median. Now this bell curve is what we call a normal distribution. So we'll say this distribution is approximately normal. We're going to spend a lot of time in this chapter talking about normal distributions and the different calculations we can do with them. Okay, so using our stopwatch data, it had a mean of 5 and a standard deviation of 1.4. Okay, I went ahead and calculated that for us. We are going to label this normal curve using that and label it 1, 2, 3 standard deviations above and below the mean. Okay, so my mean goes right there in the middle. I know it was 5. 1 standard deviation above my mean, 5 plus 1.4 is 6.4. And then if I add another standard deviation, you can see where these are marked right here. The writing's really small, but that says 1 SD, 2 SD. So 6.4 plus another 1.4 is 7.8, plus another 1.4 is 9.2. We're going to do the same thing in the other direction. 5 minus 1.4 is 3.6. Minus 1.4 is 2.2. And minus 1.4 is 0.8. Okay, the other label that we want to put on here, this is our normal notation with a capital N. And then it always is labeled with our mean, which is 5, and our standard deviation, which is 1.4. Okay, that's an important label that we'll put on our curve to show what it represents. We have a specific rule that applies to a normal curve, and it is called our 68, 95, 99.7 rule. It's also referred to as an empirical rule, and you're going to be making this nice little flip chart to represent this. So I'll be posting a separate video for you to go back and make this flip chart, but I want to show you what it represents. So in a normal distribution, we go 3 standard deviations in each direction. The area between one standard deviation is 68%. So 68% of our observations are within 1 standard deviation of the mean. 95% are within 2 standard deviations, and 97% are within 3 standard deviations. We're going to label that on this curve right here. So within 1 standard deviation, we have 68% of our observations. Within 2 standard deviations, we have 95% of our observations, out to 2 standard deviations. And within 3 standard deviations, that's 99.7% of our data. So most of our data is within 3 standard deviations. Okay, this flip book is going to become helpful because it's also divided up into like each section. So between the mean and 1 standard deviation, there's 34%. And then in this section, I have 13.5%. Okay, and that's just calculated. If there's 68% here, I divided it in half. If there's 95% here, I took off the 68 and then divided the leftovers in half. If there's 99.7% here, I took off the 95 and divided that in half. And then I also want to know how much is left out there in the tails. And it's a tiny amount, 0.15% in each tail. Okay, so if we look at these questions here, what percentage of data is within 2 standard deviations of the mean? That is 68%. Oh, 2 standard deviations, sorry, is 95%. What percent of the data is further than 2 standard deviations? So if 95% is within 2 standard deviations, we have 5% left over. what percent of data is greater than 1 standard deviation above the mean? This is where your flipbook might come in handy. So greater than 1 standard deviation is going to be this section out here. So 13.5% plus 2.35% plus 0.15% is 16%. And then what percent of the data is between z equals -1, which that is your mean minus 1 standard deviation, and z equals +2, that is your mean plus 2 standard deviations. So if I look at my flip book, so here's -1 standard deviation, and there's +2. So the area in that section is 34 plus 34 plus 13.5, which is 81.5%. Okay. And then we do have a summary of this information here on the back. Okay, we talked about our uniform distributions and our density curves in general. How do your mean and median relate with your different shapes? And then our 68, 95, 99.7 rule. So you want to make sure you get all that copied down and try this, check your understanding. And then also watch my video about your flip book, and you can make that as well.